Hello, in this video we are going to see what is an inverse matrix and we are going to try to calculate some inverse matrices. The topic is difficult because of the number of calculations but not of the type of calculations. It's not going to be so hard. Okay, so we are going to define when a matrix is called regular. This will mean that we can calculate the inverse matrix, and we will see how to calculate this inverse matrix. What do we need? As usual, we need to understand what is a matrix. We need to understand or to know how to multiply matrices and something called the Gauss elimination method, because we are going to apply it during this video. Okay, the idea is, where this inverse come from? Imagine that you have a square matrix. Let's start with a square matrix because it's going to be important that in order to calculate an inverse matrix, the matrix should be a square. And you can ask me, okay, what does this mean? What a square means? Yeah, the same number of rows and columns, okay? Then it's a square matrix. Imagine that you have a matrix equation. Okay, for example, AX equals C. All of these elements are matrices. A is a square matrix, X is a square matrix, C is a square matrix, okay? So, how can we calculate that? Imagine that X is the unknown, an unknown matrix, okay? It's not an unknown value, be careful, because it's a matrix equation, that is something different. Okay, then, the idea is, imagine that you can find another matrix that we are going to call B, such that B times A is the identity matrix. Now we are putting all topics together, all definitions together. We review what is a square matrix. The question is now, what is the identity matrix? The identity matrix is the matrix that has in the main diagonal only once, sorry, and the rest of the elements are, sorry, are all zero. Okay? So, nothing difficult. Imagine that you just found a matrix that B times A is the identity matrix. This matrix is the inverse matrix, but okay, let's keep going. So your system, your starting system, can be multiplied by B both sides. You know that when we have an equality in between, it's like a balance. Okay, whatever I do on one side, I should do it in the other part. Okay, so multiplying by B from the left both sides, it's correct. Okay, no problem. Oh, but by the way, B times A is the identity matrix, so I can replace B times A by the identity matrix. Identity matrix is like the one when we multiply, so disappears. Okay, so identity matrix times X is X. So we just solve this equation. We know that this unknown matrix is just B times C. And all is due to the fact that I just obtain a matrix such that B times A equals the identity matrix. Okay, maybe I'm doing things a little bit more complicated than expected. Okay, I'm just trying to justify why it's needed, the inverse matrix. And one application is just to solve, for example, matrix equations like the one I have here. When this happens, when I can find a matrix B such that B times A is the identity matrix, then this matrix is called the inverse matrix of A. And we are going to denote it, we are not going to write it as B, we are going to write it as A power minus 1. Okay? Perfect. So the idea is, at least the main idea I want you to retain in your mind is the following: the identity matrix is a matrix such that A times the inverse matrix is the identity matrix, and also the inverse times A is also the identity matrix. Let me write it here. Okay? An inverse matrix should verify this condition. Okay? You are always going to be given A. It's given, so you know A. And the exercise will consist in finding A power minus 1, the inverse matrix. And you must keep in mind that A times the inverse matrix is the identity matrix, and is the identity matrix. Yes, I told you right. And the inverse times A is also the identity matrix. Okay? When this happens, when I can find the inverse, the square matrix A is called regular or invertible. Okay? Nothing more than that. I think if you just understood this idea, I'm very happy, because this is the main idea of the inverse matrix. Okay, this is the definition. For sure. Calculating, it's a little bit more complicated. Okay? Come, let's keep going. More things. Square matrices that are not regular are called singular matrices. Regular is when I can calculate the inverse, singular is when I cannot. Okay? Because not all matrices has an inverse matrix. That is important. Okay? Square matrices are the only one for which you can ask yourself if I can calculate the inverse. Okay? But if they are not a square, forget about that. Okay? And even if it is a square, I still don't know. Okay? Come on, more things. Examples. I have this matrix. This matrix is regular. It has an inverse because this matrix, calculated, you don't know how, verifies that if you multiply this matrix times this matrix, you obtain the identity matrix. Do you want to check it? Do it. Okay? Spend, I don't know, 2 minutes multiplying this matrix times this matrix and finding out that the solution is ones in the main diagonal and zeros all the rest of the elements. Okay? So it's not difficult, but still you keep asking, probably you are asking me, yeah, okay, but how do I calculate that? Okay. Before we start with the process, properties. The inverse matrix is a unique element. Okay? There is no two matrices verifying the same property. Okay? Once you calculate the inverse, that is the inverse, okay, of a given matrix. Second, if we have two regular matrices, that means that if I have two matrices with inverse, then the product is also regular. This matrix has an inverse matrix. This matrix has an inverse matrix. If I multiply both, the product is also have an inverse matrix. Okay? And also the inverse of the product is the inverse of B times the inverse of A. Have you seen that the order is flipped in this case? I just had AB inverse, and this is the inverse of B times the inverse of A. The order is changed, okay? So be careful with these things, because it's very common to make this mistake. I ask you to calculate the inverse of a product, you calculate the inverse of A, multiply by inverse of B, and that is not true, okay? You need to flip the order. Next one. If A and B are square matrices, same rows and columns, and the product is regular, then A and B are regular. That is very important, okay? And the inverse has this shape, okay? I can calculate the inverse in this form. But this is a very important property, okay? If I know that the product of two matrices is regular, then each of the matrices is regular, and you can calculate it using these formulas. Okay, how are we going to calculate this inverse matrix? We can just solving a system of equations the hardest way, using Gauss method, much more nicer way, or using a formula that is called the adjoint method. All three ways are perfect. Okay, the first one is going to be not clever. Okay, use Gauss method or the adjoint method to calculate that. And also, the higher the order of the shape of the matrix, the more time it's going to take to calculate the inverse, okay? Come on, let's see an example. Let's start with something really small. 2 rows, 2 columns. So we know this matrix. A is -1, 3, 1, 0. Okay, so we are looking for a matrix that I'm going to just call X, Y, Z, and T, 4 unknowns. What is the property that the inverse must verify in order to become an inverse? That the product of these two matrices should be the identity matrix. Okay, that is the key point of the exercise. This is we are not using any method, we are just calculating directly the inverse. So I don't know what is the inverse, but I know that the product of the original matrix times this matrix X, Y, Z, and T should be 1, 0, 0, 1. So what do? We multiply these two matrices. -1, 3 multiplied by XZ is here. -1, 3 multiplied by YT, it's here. 1, 0 multiplied by x seed, it's here, and 1, 0 times y t, it's here. Okay? Two matrices are equal if, all the elements are equal. I mean, if minus x plus 3 seed is equal to 1, if minus 1 plus 3t is equal to 0, if x equal to 0, and if y equals to 1. Okay? But, okay, let's keep going. This is one of the properties of the inverse matrix, but if I flip the product, it should be the identity matrix again. So this is what I did here. The identity matrix that I'm looking for times A should be also the identity matrix. If I multiply again, I got x minus 1 plus y, it's here. The product of this row times this column is here. The product of this row times this column is here. And the product of this row times this column is here. And also I have these two matrices. This should be the same. So the first element in this matrix should be the same in this second matrix. These elements should be equal to 0. These elements should be equal to 0. And these 3 seeds should be equal to 1. So if I just separate all the equations I just mentioned, what I have is a terrible system. Okay, it's not so terrible because as you can see, many of the equations are trivial. Okay, for example, I have that x is equal to 0, y is equal to 1. But I have too many equations because I only have 4 unknowns, x, y, z, and t. So can we simplify all these equations? Yes. If we just solve the equations from here, x is equal to 0, y is equal to 1, and let's see, for example, minus z plus t is equal to 0, and z is equal to 1/3, you can replace and solve for t. So this system seems terrible, but it can be solved in 5 seconds if you just take care of what you are doing. So I have the solutions for x, y, t, and z. I just only need to put it in the right place. Remember that this was x, y, z, and t. So this is the inverse matrix. If you want to check, oh, by the way, if you want to check it, you can multiply A times this new matrix, and the solution should be the identity matrix. Okay? But we just found a way to calculate the inverse matrix. Second method, Gauss method. The idea is to write the original matrix and the identity matrix together here, as you can see. Okay, the original matrix, the one is given to you in the exercise, and the identity matrix. And using some transformations, I need to write the identity matrix in the first part, and the inverse would be the second part. Okay, it's just using the same process that we apply when we use Gauss method, elimination method. Okay, because the transformations are not changing the way or the essence of the matrix, and we can just solve it directly. Come on, let's see an example. This is going to be a little bit harder, okay? But works always. The other one for matrices that are bigger is more complicated. This one is always working perfectly. So what do we have here? Okay, we put this original matrix here and identity matrix here. So what we are going to do is to the first row is going to be changed, is going to be multiplied by -1. So as you can see, this row is multiplied by -1 and I obtain this one. And the second row is going to be the sum of the first row times the second row. So what do we have here? 1 minus 1, it's 0. 0 plus 3 is 3. 0 plus 1 is 1. 1 plus 0 is 1. So I just made this simplification and I just obtained the 0 in here and a 1 in here. Perfect. Next step. Okay, what I'm going to do is to multiply the second row by 1/3. Okay, the second row, because I want this number to be 1. So, as you can see, if I multiply by 1/3 the second row, I obtain 0, 1, 1/3, 1/3. And what else? What else? In the... nothing. I just made a mistake. This shouldn't be there. Okay, I just divide. No, yeah, so sorry. Yeah, I remember. I have a -3 in here, and this is a problem. So how do we eliminate this -3 on this term? Yeah, I was thinking. Remember that I was confused because I want to obtain the identity matrix in here. So for sure, this should be 1 in order to have the ones in the main diagonal. but the negative 3 should disappear also. So what do I do is to add in the first row the sum of the first row times the second. So let me show you. 0 plus 1, it's 1. So I just replace the first row. Then 3 plus negative 3 is 0. So I put it here. More things. Minus 1 plus 1, it's 0. So I replace the element here. And 0 plus 1, it's 1. So I leave it here. And then I multiply the second row by 1/3. So I got this. What do you see in here? The identity matrix is here, and this is the inverse. So using just 4 transformations, we just obtain the inverse matrix. Do you want to check that this is the inverse matrix? Okay, multiply A times A minus 1, and you got it. Okay? What happens if the matrix is bigger? Then you need to make much more calculations. I'm going to show you really fast here, but you can just follow the steps. The idea is that you put the original matrix here, the identity matrix in here, and after this process, I want to obtain the inverse matrix here and the final, the inverse on this side. The identity, sorry, and the inverse in this place. So the first thing we do is to subtract the third row minus the first row. So 1 minus 1, it's 0. 2 minus 2, it's 0. 0 minus 0, it's 0. Perfect. Okay, in just one step, it looks more close to the identity matrix than it was before. Okay, more things. What happened? Oh, yeah, what happened in this case? We can continue trying to put a 0 in here and a 0 in here. But it's important, I was not going to mention that now, but okay, since it appears in the slide, I'm going to mention. If all elements disappears in one of the sides, forget about the process. You are never going to be able to find an inverse. Okay? You can just keep going, calculating things. I can make a 0 in here, but how do I'm going to calculate a 0 in this position if all these two elements are 0? Okay? So we are never going to be able to find an identity matrix on this side. And how are you going to recognize? Because one row will be all zeros. Okay? In this case, then this is not possible, and we stop here. Okay, guys. What have we seen? The definition of an inverse, and we just calculate an inverse by 2 different methods. Still, the adjoint method is not seen, but I will show you in another video how to apply this method. This method requires determinants, so please be aware that in order to, when you are ready to see the next video, you review the determinants first. Okay, so guys, thank you for your attention.